related to chemical sensors in the use of uh, piezoelectric transducer like quartz crystal microbalance for measurement and sensing chemical quantities. Yeah, and today, starting from today, I think maybe for the next 2 to 3 weeks, we are going to discuss specifically about these chemical sensors, the different types of sensors that are used to detect chemical quantities or chemical parameters. And this is for biomedical engineering is quite important. Also later in the next chapter on biosensor, we are going to discuss also another important class of sensors. The biosensors basically, well, we can say that it is a subclass between chemical sensor, but some others may classify biosensors as separate, completely separate class because it it entails the use of biological molecules or compound to the sensors. While in chemical sensors and measurement, mostly it is okay or it is enough to use some form of chemical substances to detect chemical quantities. Yeah, hopefully some of you are going to do also internship in this field. Yeah, if things goes smoothly, maybe I think Tanita will do uh, some interesting internship on chemical sensors, and maybe well, Anjali is will be doing biosensors, I think, right, Anjali, if I'm not mistaken with the
Yes,
topics. Yeah. So chemical sensors are widely used, yeah, in biomedical field. So with the development of microelectronics and microprocessing, uh, then the chemical sensor itself are becoming more and more smaller, yeah, becoming smaller and smaller, more miniaturized and integrated. Yeah. And when we develop an array of an recognition element of this chemical sensor, you could also have what we have a sensor called as intelligent chemical sensor array, yeah, and which like e-nose, electronic nose, and electronic tongue. And why they are called e-nose and e-tongue is because the principles resemble those of uh, human nose and human tongue. And if we look at the anatomy of human nose and human tongue, our nose, for example, consists of thousands and maybe hundreds of thousands or even millions of receptors. Yes, tiny receptors of sensory neurons attached along the nose duct, and then each of these sensory neurons may be sensitive to uh, specific compounds, and the other sensory neurons are also specific to different classes of compounds. But together, yeah, they will respond differently towards certain smell or certain chemical compounds, and then the patterns of this recognition by these millions of sensory neurons will be conveyed to the brain, and the brain will interpret that pattern as smell. So that is why we can smell whether it is the smell of coffee, it is the smell of perfume, the smell of durian, for example, the smell of a rotten fruit, etc., etc. Yeah, using our nose. Similarly, our tongue also consists of millions or hundreds of thousands sensory neurons, yeah, at the various parts of the tongue, and some part of the tongue may be sensitive towards salty taste, the other part may be sensitive towards uh, sweet taste, the other part sensitive towards sour, or the other part sensitive towards bitterness, etc. And when we are chewing our food and they are interacting with the chemical compounds of the food. Okay? And then the recognition element will interact differently between these different parts of the tongue, and then the pattern of the recognition of the signal from our tongue is conveyed to the brain for recognition. So they use different ways of basically doing the sensing instead of relying on a single recognition element, like most of the conventional sensors do. The tongue and the nose work by orchestrating an array of hundreds of thousands of sensory neurons, yeah, to recognize at the same time. And of course, the pattern will be different. And based on our learning process during our upbringing, we can smell that our brain can differentiate between the different patterns of the smell. And many of the currently developed electronic nose and electronic tongues are developed using that principle. Like you see the Genos, the electronic nose developed by researchers from Universitas Gadjah Mada, and it is developed from an array of sensor, of gas sensor. And gas sensor is basically a type of chemical sensor, yeah, that I think eight consisting of 8 elements, or a little bit more, or 16, I forgot. And this Genos recognize the pattern of the different gases, different volatile organic compounds that we breathe out. Yeah, because you breathe out and you exhale, and you fill in that what do you call it, that bag, yeah. And then that bag is you put into the machine. Then the machine will recognize the compositions of the gas that you exhaled from your body, and then depending on the condition, the metabolic condition of the lung, then the gas that coming out of the lung will be different. Okay, so then the Genos is trained using artificial intelligence, using machine learning algorithm to differentiate between healthy and positive COVID patient breathing pattern. Okay, so this chapter will introduce you to the principle and characteristic of the some typical chemical sensors that are widely used in the industry, in the market, and also by medical field. Among others, they are the ion sensors, the gas sensors, and the humidity sensors. And we will also present later introduction to electronic nose, electronic tongue, microfluidic chips. I myself I am specializing in microfluidic, also using fabric-based devices, and a little bit introduction on wireless sensor networks. This is maybe the specialization of Pak Aulia. So the first chemical sensor can be traced back to 1906. This is pioneered by a person called Kramer, that he discovered on the phenomenon of glass thin films responding to hydrogen ions in a solution, and invented the glass electrode to measure pH. So pH is one of the oldest chemical sensor. Actually, we are using it, right? In our lab, we have some pH devices. Yeah, that however, the research on this chemical sensor progressed slowly, and then there are after pH sensor, then we have the study on humidity sensors. Okay? And since 1960, many different chemical sensors are invented, yeah, like ion selective response to detect the presence of ion in a liquid sample, just using silver halide and zinc oxide, two flammable gases, the beginning of the invention of gas sensor. And then we have we after that there are many new materials and principles in the 1960s, 1970s. being invented, that uses acoustical sensor, optical sensor, as well as pressure sensor using, as I mentioned, some of them, for example, using acoustical sensor that uses the principle of piezoelectric transducer as the transducer. Then the transducer is being coated by either membrane or other chemical compound to make it selective and sensitive towards certain compound. Similarly, optical sensor-based chemical sensors are also being invented, where the response is in the form of optical change, in the form of optical change, either color change or color intensity change. Then the ion selective electrodes continue to be developed as one of the oldest electrochemical sensors, like electrochemical sensor. And now that during that period, almost 90% belongs to the ion selective electrode class as one class of chemical sensor. Then after in the 1980s, since the development of IC, integrated circuit using microelectronics technology increases rapidly, then some of this development fabrication technology, manufacturing technology of chemical sensors also started to use this microelectronic technology, and they start to be miniaturized. Okay. Then especially the electrochemical sensors, because electrochemical sensors converts any chemical reaction or changes into electronic change. So in what is important, besides all the parameters that you have learned in some earlier chapter about sensor characteristics, of course you have learned about sensitivity, you have learned about time response, fast response. And what is also important in chemical sensor is what we call as selectivity. Selectivity is in traditional chemical sensor, usually we want that chemical sensor to be selective, to be sensitive only to particular chemical compound or chemical substance. For example, at pH, we want it only to be sensitive towards hydrogen ion, H plus ions or OH minus ion. And ion selective electrons, depending on the membrane that you cover the electrode, you want it to be selective only to certain type of ions. You don't want it to be sensitive towards all ions. Okay. So this is what selectivity is about, where the sensor is sensitive only towards some specific substance or analyte compared to the other. So it should have low sensitivity compared to the other competing compounds within the sample, but high sensitivity compared to that particular compound of interest. So selectivity, some define it as this ratio of the device of the chemical sensor toward that, let's say, the analyte, and compared to the sensitivity of other analyte. So while I here to 1, 2, 3 until n. So all the other competing analytes within that sample. So let's say we want to only detect sodium ion in our saliva. So when we people what is the selectivity towards the sodium ion compared to other ions within the saliva. So you have then also to do experiment testing the sensitivity of the sodium ion in for to sensitivity of that sensor towards sodium ion, but you have also to test its sensitivity towards other competing ion, chlorine ion, potassium ion, what else, and other ions. When your device shows relatively very high sensitivity towards sodium ion compared to the other existing ions within the sample, then you know that it means your sensor, your device is selective towards sodium ion. Then we have wide measuring range here. So wide measuring range means that how much range of concentration. Usually when in quantitative chemical sensors and measurement, we are also interested to the quantity or the amount of the chemical compound or chemical substances within the sample. And this shows the wide measuring range. So whether it is from 0 to 100 millimolar, or 0 to 1 molar, for example, 0 to 10 micromolar, or what. So usually ideally we want it to be able to be sensitive in all the range that the that the particular analyte of interest can have in the particular sample. But practically, that is not possible. Usually, it will depend on so many factors. Yeah. So usually, either we have the range is very small, very linear, and very small, but you could have very wide, a little bit wide, but then the response is not linear anymore, etc., etc. Yeah. And this has been used, the chemical sensor, actually now in environmental protection and monitoring to detect the presence of heavy metals, for example, in the river. Is in the industrial and agricultural production, for example. I know one of my friends in Thailand, they developed, his group developed capsaicin chemical sensor, yeah, to detect the amount of capsaicin in food. Anyone of you know what capsaicin is? Angeli, Ezra, Anita, do you know what capsaicin is? Ezra, ever heard about capsaicin?
To be honest, no, sir.
Anita,
No.
never. Angeli, maybe
Belum pernah dengar juga, sir.
the first time you heard this,
Iya.
but maybe you eat it every day. You know what capsaicin is? You eat it maybe every day. Maybe if you like to eat spice, if you like to the spice taste in Lombok, okay, in cabe, yeah, in sambal, then it should have this compound capsaicin. Yeah. Any of you do not like spice taste? Everyone likes.
Yes, sir.
Yeah.
So capsaicin is in those spicy taste. Yeah, every vegetation that has spice taste, either paprika or cabe or whatever. What is cabe in English? By the way? Lombok, yeah, or any spicy plant, any spicy plant, they usually have capsaicin. So this friend of mine in Thailand, he developed a chemical sensor that detects the presence of capsaicin, how much amount of capsaicin in particular processed food in industry. So to have, to be able to have quality control of their processed food, yeah, of their processed food. So and actually, yeah, this is just one example. Yeah, our tongue of also actually when we are sensitive towards spicy, especially those people maybe who cannot eat spicy food because they have too sensitive sensor towards capsaicin. Yeah, they feel burned. Yeah. But I used to be like that actually in when I was child. But when you can train later your electronic tongue, your tongue to be able to desensitize it. So people who can eat very spicy people usually their sensory neurons in their tongue is already desensitized, not sensitive, not to have very high sensitivity towards capsaicin. That's why they can endure very spicy food. Yeah. So Coming back to the discussion, yes. So this chemical sensors can be used to quantify and provide quality control in food, yeah, to detect the amount of capsaicin in industrial or agricultural production. That's why it is also used in food testing. Weather forecast, maybe, yeah, from the content of moisture, of humidity in the atmosphere, and then from there, then you can forecast weather. And what we are concerned of course, for healthcare and diagnosis of disease. Yeah, that's why all of this has become the trends and become subjects of development, yeah, in the field of contemporary analytical chemistry. So here we see the different fields, yeah, in our life that is being affected by the development of chemical sensors. And actually, it is I think also more fields are being affected by chemical sensor and later by chemical sensor, by sensor, compared to the fields that are affected by physical sensor. Yeah, because even in our body, many of the biomedical parameters are in chemical domain or in biochemical domain. Okay, but when we see in our world now, why is there not so many chemical sensors around? For example, in our smartphone, why are there only mostly physical sensors? Yeah, in our smartphone, maybe there is a pressure sensor, there is microphone, there is magnetic sensors for compass and accelerometer and gyroscope. But why isn't there any chemical sensor inside our smartphone? Yeah, the answer lies later when we start to study many of these different types of chemical sensor. It is not that easy to develop and fabricate a good chemical sensor. Yeah, yeah, you have more, as we have see here. You have many other parameters to be concerned of. Yeah, where is it? Yes, now you have the sensitivity aspects, you have the selectivity aspect, the range, yeah, the range of the sensors that you need to be concerned of, and many others. Yeah. And it could disappear. Uh, uh, yeah, this one. Yes. You have the not only sensitivity that you are concerned of, the time response, wide measuring range, also the selectivity. In many of these chemical sensors, compared to their physical sensors, yeah, chemical sensors have lower time response. They are not that fast. Yeah. That is why their use is also not that widespread. They cannot also it is not that easy to use chemical sensor in continuous manner because of that slow response. But it is indeed can be used in many different industry. That is why the subject of chemical sensors, I think, from my personal perspective, maybe subjective perspective, is that there are still many rooms to develop and to research in chemical sensors and also biological sensors compared to the physical sensors field. Okay, this one about the meetings. Yeah, there are also specific international conference on chemical sensors, and also in general conference on sensor. Usually, you have some session specific towards the development of chemical-based sensor, chemical sensor. Okay, let's see here some definition of chemical sensors. Yeah, defined by previously by some experts. So this is the general description that chemical sensors are small size devices comprising of recognition element, a transduction element, and a signal processor. So three different elements within a single sensor. And this is also usually true later for biological sensor. Only the recognition element in biosensor will be mostly comes from biological molecule or biological tissue. Later we will study in the next chapter. And the chemical recognition element itself cannot produce signal that can be read by our microprocessor, right? That is what it needs, a secondary code transducer in the form of transaction element, which will convert any physical signal, physicochemical signal produced by the recognition element into electronic signal, into electrical information, electrical signal. And then further, the signal will be processed by a signal processor capable of continuously and reversibly reporting the chemical concentration. So this is the general illustration graph of chemical sensor, the flow, the signal flow diagram in a chemical sensor. You have the analyte, as I mentioned earlier. It could be, for example, as simple as old as pH sensor, where you have the analyte. In this case, will be H plus, or maybe you want to detect chlorine ion, you want to detect sodium ion, or you want to detect a chemical as complex as the volatile organic compound. Yeah. This is gas that is in the exhaled breath of a patient, of a COVID-19 patient, for example. And then these analytes will be recognized. First, will be captured by or will conduct chemical recognition reaction with the recognition element. So the recognition element usually will be in the form of chemical compound. Either it can be a membrane, okay, it can be a polymer coating, another polymer coating, or many others. It could be also zeolite. Zeolite could be also a semiconductor, and for example, in the case of gas sensor, semiconductor ceramics, semiconductor, and many others. So usually, then this will produce a chemical quantities, in the form of, for example, in the case of membrane, it will produce some compound. In the case of enzyme is actually already a type of biosensor. It will create another chemical product, and this will be recognized by a transaction element, which will recognize, for example, the heat from the reaction, or color change, right? or light intensity change, due to the chemical reaction. From here, the transaction element will convert it into useful electrical signal. So if you have heat, then you will put a thermistor, for example, a resistor that is sensitive towards thermal change. If it is color change or light intensity, you could put photodiode, photoresistor, phototransistor, which will change then any of the light intensity change into voltage change or resistance change. And then this can be further processed using signal processing, either in the analog domain or the digital domain. So the definition by EUPAC, International Union of Pure and Applied Chemistry, is more in general. Chemical sensor is a device that transforms chemical information ranging from concentration of a specific sample component to total composition analysis into an analytically useful signal. So this is more technical, while the previous definition is more practical, a pragmatic definition. But in the definition by Wolf-Weiss, it is more showing towards the elements comprising a chemical sensor. Okay. So as a kind of analytical device, chemical sensors are so effective that they can detect the object molecules in the presence of interfering substances. This is important. In the presence of interfering substances, this is what I mentioned as the selectivity. So even there are many interfering substances, a good chemical sensor, in conventional definition, later I will I will explain why conventional and the current trend towards different way of what comprises a good chemical sensor. In the conventional way, a chemical sensor should be able to detect the object molecule of interest in the presence of other interfering substances. This is what we call as selectivity. Okay. Okay, then the classification of chemical sensors. This one. So you have ion sensors. This is basically in the form of ions in a liquid, and this can be detected with different ways. The oldest way is the ion selective electrodes, as I mentioned, and this goes back to the development and invention of pH sensor, a pH sensor that can detect hydrogen ions specifically. Then we could have ion selective field effect transistor. This is FET, that is selective, that is covered by, for example, membrane or other compound or other substances, polymer, that can bind or that can react specifically to particular ion. And that makes then the response of the FET will depends on the presence of that ion. Then we have light addressable potentiometric sensor. This is more of radiation-based chemical sensor. Then microelectrode array, detecting the potential due to the presence of the sensors. And we have chemical sensor in the gas phase, the gas sensor. Gas sensor itself, based on their principles, can be classified into electrochemical gas sensors, where electrochemical reaction occurs between the gas of interest with the compounds in that gas sensor. Semiconductor gas sensor, I have mentioned this, where usually it is made from metal oxide ceramics, and it is usually in polycrystalline material, and the gas will interact with the surface of that semiconductor, and there the semiconductor usually has vacancies or defects, and then the gas can interact with the defects to produce free electrons or free holes. We have solid electrolyte gas sensor. This consists of electrolyte, but in the solid state phase. Then I have also maybe slightly mentioned when we discuss about piezoelectric sensor, surface acoustic wave sensor, where we operate the piezoelectric sensors as an acoustical wave source to generate acoustical wave, and from there, when we coat the acoustical wave piezoelectric sensor with certain coating that can interact with particular chemicals, then we can make that surface acoustic wave sensor to be a chemical sensor. In the case, usually it is easier to react with gas sensor, although there are also surface acoustic wave sensor or acoustic wave sensor that are used to detect chemicals in liquid phase. Okay, and when we mention here surface, actually there is also a type of sensor that is using not on the surface phenomena but bulk acoustical wave. We call it bulk acoustical wave sensor. Okay, so many different types of this gas sensor. Then we have humidity sensors. It can be either a capacitive humidity sensors. We have mentioned this during the maybe slightly when we discuss about capacitive sensor. The electric material, for example, if we make it porous, it can absorb water vapor from the surrounding atmosphere. Then it will be sensitive towards humidity. The epsilon R, the relative permittivity of the dielectric material between the two electrodes, the value will change depending on the water vapor content of the surrounding atmosphere. Then we can function that capacitor as a capacitive humidity sensor. Resistive humidity sensor also similar, but in this case, then we measure the resistivity, the resistance change instead of the capacitance change. Thermal conductivity humidity sensors. So this detects the upon absorption of water vapor, the thermal, how the material conduct heat will also change the thermal conductivity property of the material. And therefore, it can be used to detect also humidity sensor from this thermal conductivity. So you see here that chemical sensors, actually, they are very much related to the material properties, as well as the related physical-chemical principle or chemical-physical principle being used. Yeah. So many of these chemical sensors are based on the selective screening, a selective what do you call it, filtering of the chemicals, and then from there they are then being transduced into the physical transducer, either using electrode or transistor, potentiometric or radiation sensor, light, etc. While some other depends on the electrochemical reaction between the analyte and the material of the chemical sensor. So chemical sensors should be able to transform the chemical quantities into electrical signal. Should be able to respond rapidly. Yeah, and this is something which is actually not that easy to obtain. Yeah, to attain in the development of chemical sensor, and it becomes one of the greatest challenge. Yeah, you could make the chemical sensor to respond rapidly when you miniaturize the sensor and also maintain their activity over a long time period. And then should also be small, be cheap. Yeah. Cheap can be obtained when we can mass produce a sensor. And this one, something which is maybe only in, well, that we have also actually similar in physical based sensor, but this is more relevant and more important, more significant in chemical based sensor, specificity and selectivity. They should respond exclusively to one analyte or at least be selective to a group of analytes. Although this changes in the recent days, yeah, with the increasing development in electronic thumb and electronic nose, you do not really need to have a specific sensor towards one analyte. What you can have is you have an array of recognition element that can recognize the pattern of different analytes. And then you use the artificial intelligence or machine learning algorithm to recognize the pattern. And this is something, well, actually not that new, yeah, but with the advent of more processing powers with computers and this class of chemical sensor, yeah, using an array of recognition elements is becoming more and more popular and more developed, being more and more being researched. It's become a trending research topic now. And another reason why it is, so one is it is easier to train a multiple array of not that specific recognition element to make them into a chemical sensor that can recognize the presence or the quantity of certain analyte, like what we have seen with the genos case. But on the other hand, also it is easier to make that kind of array of chemical sensor, which is each of the recognition element does not need to be very selective towards that analyte. Because to have a very selective recognition element to a particular analyte, like what this condition demands, usually it requires specific manufacturing technique or development technique. Yeah. For example, you need to use antibody or you need to use molecularly imprinted polymer MIP and many other techniques. Yeah. And for common chemicals, it is not that difficult. But now, with so many different things in the that we come in our environment and settle many new chemicals, it is not that easy. Okay. The above list can be extended with, for example, the postulation of a low detection limit or high sensitivity. That means that low concentration values should be detected. And low, this is basically related to the high sensitivity or the high resolution. Are there any questions or comments or critics regarding chemical sensors? This is still introduction. So next week we will go to each class of this chemical sensor. Any comments, questions, maybe?